Welcome to Lesson 18, Resistivity and Circuit Components. Here's the plan for today. I like to think of electrons as a crowd leaving a festival, squeezing through a passageway. Two things make it harder to get through. A longer passage means more distance to fight through. A narrower passage means more crowding and more collisions. Widen it and everyone flows more easily. That is exactly the resistance of a wire. R equals rho L over A. Resistance goes up with length and down with cross-sectional area. And rho, resistivity, is a property of the material itself, measured in ohm meters. This is a specific constant for each material. The range of resistivity values between different materials is staggering. Copper is around 10 to the minus 8 ohm meters. PVC, the white plastic used in bathrooms, is around 10 to the 14. That is 22 orders of magnitude between a good conductor and a good insulator, which is precisely why we make wires out of copper and coat them in plastic. What does heating a metal do? The metal ions in the lattice vibrate more vigorously. The electrons trying to drift past now collide with them far more often, so it's harder to get through and the resistance rises. Hotter metal, higher resistance. Remember, that's the opposite of a semiconductor. But cooling a certain type of material, a superconductor, down far enough and something remarkable happens. Below a particular critical temperature, the resistance doesn't get smaller, it drops sharply to exactly zero. The way I like to think of it is when the temperature is cool enough in a certain material, the electrons now pass through the material like ordered lines in the crowd. The channels never collide at all. Zero resistance means zero energy lost as heat, which is why superconductors matter so much for things like MRI magnets and lossless power transmission. However, the materials are very expensive and need to be cooled to a very low temperature, so they're not really used that much in our daily lives. Which brings us to the thermistor, specifically the negative temperature coefficient type, which is the one that you need to know. Its resistance falls as temperature rises. This sounds unintuitive, but heating it causes charge carriers to be released, sort of like releasing the electrons from being held by the atoms. This unblocks more paths for the current, and is exactly what we said about semiconductors last lesson. So a thermistor behaves the opposite way to a plain metal wire, and that opposite behaviour is what makes it so useful as a temperature sensor, as we'll see when we build potential dividers. Do note that there are also positive coefficient versions, but these just behave like normal resistors. There are 11 circuit symbols that you need to know, and there's not really any shortcut to learning them. The main four are the cell, the lamp, the voltmeter, and the ammeter. The four types of resistors are fixed, variable, thermistor, and light dependent, sometimes given as LDR. And the others, motors, heaters, and diodes, also called LEDs. There's one important practical point that comes up in experiments and in exam questions. The ammeter goes in series because it has to sit in the flow to measure the current going through. The voltmeter goes in parallel across the component you're measuring because it measures the difference in potential from one side to the other, the drop across it. Series for current, parallel for voltage. And the resistance of an ammeter is near zero because it doesn't want to affect any of the circuit. But the resistance of the voltmeter is near infinite because it doesn't want any electrons to flow along it, just through the component that you're trying to measure. Now on to the graphs. Current against voltage for the components that you need. First, an ohmic resistor, a straight line through the origin, meaning current is proportional to voltage and the resistance stays constant. Note that when we say an ohmic resistor, we just mean one that obeys Ohm's law, V equals IR. The filament lamp is an S-shaped curve. As more current flows, the filament heats up, and as we just said, a hot metal has more resistance. So the graph bends over because you get less and less extra current for each extra volt. Note something about both of these. They have rotational symmetry. Flip the voltage the other way and the current behaves identically in reverse. They don't care which direction you push. Lastly is the diode, which has near zero current when used in reverse. But in the positive direction, it must overcome a certain voltage for electrons to allow to be pushed through. Let's look at that now. The best way to describe the diode is a one-way valve. In forward flow, above around 0.7 volts, current can flow easily through. But in reverse flow, trying to push against the one-way valve, the gates essentially close, so it's very hard to flow in the other direction. Only a small amount of current is let through. That's the end of the video. Next time we put these components together and work out how current and voltage share themselves around a circuit. Thanks for watching, and check out my tutoring page below.